We will see how a fracture criterion is expressed in terms of stress intensity factor. And this is a criterion for brittle fracture. It's especially applicable for such materials that display brittle behavior. It is referred to as the critical stress intensity factor, fracture criterion, or simply a fracture criterion for mode 1 problems. We will talk about mixed mode later. We know how asymptotic fields dominate character fields. This is the general representation of stresses, asymptotic stresses at the character. There is the square root singularity, 1 over square root of 2 pi r, times a function of the polar coordinate theta, and K1 is the strength of singularity. It's named as the mode 1 stress intensity factor. And this fracture criterion postulates that brittle fracture occurs whenever the mode 1 stress intensity factor shown here reaches a critical value. That critical value is a material property. It's called fracture toughness of the material. And this is applicable if the singularity dominated zone, asymptotic zone, encloses the zone associated with plasticity and large strains. There's a zone at the character associated with plasticity, but the summary of this fundamental law of linear elastic fracture mechanics. In linear elastic fracture mechanics, basic parameter is mode 1 stress intensity factor. A component will fail in brittle fracture if stress intensity factor reaches a critical value. This critical value is a material property. And this is applicable for brittle materials, or materials displaying this brittle behavior under certain temperature or loading conditions. But the requirement is that the asymptotic zone, the largest zone here, which is designated by STZ, singularity dominated zone, circumscribes an inner smaller zone in brittle materials. In this smaller zone, plasticity occurs. Therefore, the linear elastic concept is not valid in this smaller zone, which is referred to as fracture process zone. As long as fracture process zone is much smaller compared to the asymptotic zone, this fracture criterion is applicable. And this happens to be the case for brittle materials, or materials displaying brittle fracture behavior, such as ceramics or metallic materials under certain temperature conditions. But it could be an accurate way of predicting fracture of a material which contains a crack or a defect. And that is called fracture criterion, and mathematical representation, of course, from an engineering point of view. K1 equals Kc. At the point of fracture, stress intensity factor for a mode 1. Right now, we are talking about a mode 1 crack. The stress intensity factor should reach a critical value, which is Kc. And Kc is named as fracture toughness of the material. Now, this is strongly dependent on the material, of course. Is it an aluminum, steel, titanium, ceramic? What is the Kc value? Kc is determined through standardized tests, as named as fracture toughness. But it also depends on some other geometric factors such as thickness. We will talk about it in more detail, and also it's affected by the loading rate. We have considering static loads, but there are also dynamic loads. Impact type loads are stresses applied in a short period of time. But our criterion is going to be K1 equals Kc for crack initiation or brittle fracture. This representation is valid. And how can we apply this to examine fracture behavior of materials? And we will see it over certain examples. First, this somewhat simple scenario where K1 is given as beta times sigma times square root of pi a. Now we are looking into a general geometry where geometry factor beta itself is known or should be known. It's beta. And for stress intensity factor is beta sigma square root of pi a. A is the crack length. When does fracture occur? It occurs when K1 equals Kc. This is the fracture toughness of the material. And the first line here is K1 versus sigma line. Like K1 is linearly dependent on sigma. Therefore, it increases linearly as we increase sigma. And this is for a given crack length. Suppose that crack length is A1. And when does failure occur? It occurs at this point, the intersection point, K1 equals Kc. And what is the failure stress for this crack length? This is the failure stress. And failure stress is known as critical stress in fracture mechanics or in failure applications for a given crack length. Failure stress is known as critical stress. And you can consider a somewhat smaller crack length, a line with a smaller slope, and you will observe an increase in the failure stress because the intersection is shifted to right. This is the failure point, and therefore fracture occurs for this stress level. And you can continually change the crack length or even a smaller crack length that is going to be the point of fracture, and much larger failure stress is predicted by this concept of linear elastic fracture mechanics. Yes, if it is too small, I mean, it should be at the macro level, and you can use standard engineering measurement techniques for those macro level dimensions. It's not micro level void or defect, it's at macro level. And those crack lengths, of course, that's an important point because it will affect your prediction. Everything depends on the crack length. And here we can see that A1 is greater than A2 and that's greater than A3. And that is one way of demonstrating this result, fracture criterion, which implies that K1 equals Kc, fracture toughness. It's a point of fracture. And there is another way of presenting these results, and it is also referred to as failure locus diagram. Again, general representation for mode 1 stress intensity factor is K1 equals beta sigma square root of pi a. And what is our fracture condition? I can type it here, K1. K1 equals Kc. That is or beta sigma square root of pi a equals Kc. and write sigma in terms of A. It's not typed here, but this implies that sigma equals Kc over beta times square root of pi A. Is that right? That's going to be your failure curve. This implies that at the point of failure, sigma equals Kc over beta times square root of pi A. And this curve is, this graph is the graph of that equation, sigma equals Kc over beta times square root of pi A. This is our graph. And if you increase Kc, it will shift in this direction. And now, this is a failure locus, which means that if this is the stress level applied to the specimen, then it's going to be, it will be fractured for this crack length. And that's going to be the critical crack length. If we have a specimen and applied stress is known, the question is, at what crack length will it fail? It will fail. And the answer is sigma equals Kc over beta times square root of pi A. That equation, Stall's equation for A, and you'll be able to find critical crack length. Or the reverse procedure, we can be given a specimen with a certain crack length. Crack length is 2 centimeters, and fracture toughness is given 100 megapascal square root of meters. What is the critical stress? At what stress the specimen fails by fracture? And that is, again, that can be found from the failure locus. Therefore, this is the safe region here to the left of one graph. The specimen is safe. The outer region is the failed region. From fracture point of view, cracked specimen is safe is if sigma A combination falls into this region. This is not safe region, of course. And we can draw these graphs or failure loci on different types of specimens. And there is an example. I think we can quickly, we don't have much time, but we can quickly go over this. A panel is given, a center cracked panel is given. Width and thickness are provided. Crack length is given as 3 centimeters. This is our panel. It's under the effect of stress sigma. Crack length, W, and thickness are known. Yield strength is given. Sy is 415 megapascals. And fracture toughness is also given. 55 megapascals square root of meters. Now, fracture toughness, this is a function of thickness. So for this particular thickness, this value is given, 55. Now, at what value of stress failure occurs? What is the failure stress? First, we can apply fracture criterion. K1 for this specimen is beta sigma square root of pi A. Beta is given for a centrally located crack. Total crack length is 2A. 2A equals 3 centimeters. W is 10 centimeters. Therefore, beta is 1.054. Beta is known. A is known. Kc is known. Therefore, calculate sigma. Equate this to Kc. Calculate sigma critical, which is given as 240.5 megapascals. For this specimen with a crack length of 3 centimeters, failure stress, fracture stress is 240 megapascals. Now, for such a structure, I can also consider plastic collapse or failure by yielding. Total plastic collapse. Does it occur before fracture or just after fracture? It's possible to find the stress that causes failure due to plasticity. Now, this can be done. Now, remote stress is sigma. Define this average remote stress as sigma equals P over B times W. W is total width, B is thickness. And define a net section stress for the cracked cross section. For this cracked cross section, cross sectional area is smaller. It is W minus 2A times B. And define an average stress for that cross section as sigma net equals pure B times W minus 2A. That's different at the cracked section. Now the ratio sigma over sigma net is then W minus 2A over W. And at the point of plastic collapse, sigma net equals sigma yield. Therefore, our equation for failure by plasticity is W minus 2A over W times Sy. Therefore, for such failure, this is found as 290 megapascals. I have two failure stresses: failure due to fracture. Critical stress is 240 megapascals. Failure due to plastic collapse. Stress is 290. 290 versus 240. So, does failure occur by fracture or plastic collapse? By fracture, right? Because it's smaller stress. You are increasing stress. It's fail by crack propagation and fracture. And an inverse problem is also defined. Once failure stress is given, you can find the failure load as well. Load is stress times area, around 300 kilonewtons. The inverse problem, stress is given and critical crack length is asked. That's the inverse problem. Suppose that somewhat larger stress is applied, 260 megapascals. Our crack length is not known. What is the largest crack length that the specimen can support? Here's the question. But we are following exactly the same procedure. Use fracture criterion. Beta sigma square root of pi a equals Kc. Now a is an unknown and it is a nonlinear equation in terms of a. Because beta is a polynomial type of equation and you have square root of AC as a result, and a nonlinear equation which can be solved easily by a math package, or you can use your own code. So after solving by Maple, I have found critical crack length 1.31. Half crack length. The total crack length is 2A for internal cracks. Be careful about it. Crack length at failure is 263 centimeters. But this is for fracture type of failure mode. What is the maximum crack length and load if the failure is by plastic collapse? And carry out the same analysis. Sorry. Sigma W minus J over W times Sy. And for this crack length, plastic collapse stress is larger. It is 306 megapascals. Therefore, again, it doesn't fail by plastic collapse or fracture. Failure mode is fracture because larger stress or plasticity, or Another way of arriving at the same result is applied stress is 260 megapascals. At the point of full-scale plasticity, this is 1 minus 2 over W times Sy. Therefore, crack length required for plasticity is half crack length is 1.87 centimeters, which is larger than this, so this occurs first. Fracture failure occurs before plasticity. That was an illustration of fracture criterion. The equation is K1 equals Kc. And you can apply that equation to predict the onset of fracture. The stress required to be applied at the point of fracture can be calculated. That's called critical stress. Or if stress is given, you can find crack length at the point of fracture. It's called critical crack length. That's an important parameter because fatigue failure, for example, occurs at the point of critical crack length. We will talk about fatigue problems later, but there could be a crack. It's going by fracture. And at which point will this crack fail? It will fail when A equals A critical. When A reaches the critical value. And how is the critical value calculated? We have shown this. And that is one of the important criteria considered in predictions of fracture mechanics. Any questions about these results? I'm going to stop the recording if you don't have any other comments.